Next speaker is Professor Gwo Ching Wang from Rensselaer Polytechnic Institute. She's the Travel Study Institute Chair of Physics, Applied Physics and Astronomy. Research focused on growth, characterization, and physics of thin films and nanostructures using state-of-the-art techniques. She's going to talk about ultra-thin layered materials studied by AFM and MFM.
Okay. I'm Gwo Ching Wang. I'm from RPI Physics. I'm very pleased to be here to share with you some of our recent work and some older work. I also want to highlight the collaboration with Dr. Xie at Park, which is the magnetic force microscopy work. So the outline is the following. I will first talk about the van der Waals force. We already heard about a little bit about van der Waals material. Then I touch upon a little bit about van der Waals epitaxy. Then I will give two examples. One is using atomic force microscopy to study the strain relaxation in a very soft perovskite material on layer mica substrate. Another example is a magnetic force microscopy study of the layer material, which is a vanadium disulfide on SiO2. Then I thought maybe I can share a finding from my former students, which I think is very nice related to the AFM work, but I think it's a little bit under publicized. I hope I will share with you that how do you quantitatively describe a rough surface from AFM image. So the first example was introduction about the van der Waals epitaxy. Say, for example, you have a graphite, which is a layer material. Between the layer of graphene, you have very weak van der Waals interaction. It consists two parts. One is the repulsive part, which is 1/R12. The other one is attractive 1/R6. So this repulsive and attractive force add together give you the one van der Waals force. Now, if you put a one van der Waals material on top of another van der Waals material, you form an interface. The question is that this van der Waals interface, would that introduce any strain on the van der Waals material you put on top of the substrate? So the example I'm going to talk about is a perovskite, which is very soft, means very easily stretched, okay? Which is a direct band gap semiconductor. So hopefully we'll find a use in the future. And mica, as everybody knows, it's very easy to peel off, like Alan just demonstrated in his PowerPoint, okay? Now what's the advantage about is the van der Waals material grows on van der Waals substrate. You can imagine because the interlayer spacing, despite its several angstrom, but its interaction very weak. So you can imagine it's just throw an ice cube on an icy lake, okay? They should be incommensurate, free floating relative to each other. However, the example I'm going to show you, the perovskite, which is grown by CVD by my colleague in material science engineering. There are two thickness regimes. One is the very thin flakes. As you can see, they form very nice regular shape, okay? And if you use AFM to scan one of the flakes, you see it's very nice, sharp step up, then smooth surface. No matter it's I cannot even see 13, 17 nanometer or thicker, okay? Now, the feature is there's no holes. But if you look at the thicker flakes, which is over 100 nanometer, immediately you see holes, large, small, also additional cracks. But the overall, the shape of the hole still along two, almost a 90-degree direction, okay? So if you just zoom in one of the flake that has holes in the middle, okay, and you scan across this direction, you find that it has very nice atomic spacing between each terrace. So this is very surprising, because when my colleagues started, they saw this perovskite is a non-layer material, but this AFM data shows that it can form very nice monolayer structure with terraces. Okay? This is published early this year. Okay? So we all know that when you have a film that has cracks or holes, it's an indication that there's a certain strain that gets relaxed. Actually, if you look at lattice constant between the perovskite and mica, they're about 10% difference. So next slide shows the photoluminescence study from different thickness of flakes. This is the thinnest one. The peak of the PL is about 2.44 EV. When you increase the thickness of flakes to maybe 30 nanometer, this peak is almost like the bulk photoluminescence peak. So this photoluminescence data attached with the flakes you just saw has a hole there. That implies that there's certain strain relaxation. We all know that PL change is related to the electronic band gap change. And electronic band gap change is associated with the detailed atomic structure. So a colleague in the area with first principle density function calculation actually did a calculation of the interface. So the bottom is potassium, because the mica is known to terminate at the potassium layer. The top is the perovskite that has a seizing bromine PB. So as you can see, this is not a very regular interface. There's certain distortion. That distortion is related to the strain between the perovskite and the mica. The series even did a total interaction energy calculation. This part includes both ionic and van der Waals. And this part is this ionic and van der Waals. As you can see, there's a huge percent, I should not say, 27% of van der Waals interaction, but majority is ionic. So even though we thought mica is a layer material, okay, should be served as a van der Waals substrate, doesn't have a lot of effect on the overlayer, but this example shows that it's not. Mica actually has very strong interaction with the perovskite that is grown on top of it, okay? All right, now I'm going to change the topic, talking about a different material. This is a transition metal dicarbonate, TMDs. And from this MRS bulletin work, I took part of the information. Basically, you can have metallic, semi-metallic, and semiconductor. And if you categorize the metallic TMDs, there are many, many of them, okay? For example, VS2, VSE3, and VT2, okay? Now, in terms of semiconductor, most famous one probably molybdenum disulfide and so forth. And they have a lot of application, interconnect, Josephson junction for metallic one. For semiconductor one, there's also a lot of applications, okay? And if you have those TMDs material in a bulk format, they're mostly paramagnetic or diamagnetic. So the information I'm going to share with you in the next few slides is that when this TMDs material goes to very thin, either monolayer or film layer, they actually has magnetic property. So this theory actually is ahead of experimental work. The first principle density function calculation has done several material, for example, VS2, VSE2, and VT2. And they found out it's in this three case, okay, sorry, has three, like this three cases that has the magnetic moment mu sub B, okay, which is ball magneton, around half ball magneton, Okay? So people are interested to measure this VS2 or VSE3 and see if they have real magnetic property. The reason they have magnetic spin is because this ampere D electrons in the transition metal, in this case vanadium, okay, that when you break this metal, transition metal, and this sulfur or selenium bond, okay, this ampere D electron gives that extra spin. So I'm going to show you some experimental work. Okay. This one on the left is vanadium disulfide monolayer on this graphite, okay, and measured by vibrating sample magnetometer. Okay. They also did this VSE2 on molybdenum disulfide, but I'm not going to show you that data. And this just published earlier this year. Okay. So they have very nice hysteresis loop, both at room temperature and low temperature. Okay. Now, for this VS2, instead using MBE method, the thermal, hydrothermal method, which can give you nanosheets, not a monolayer, between, say, 1 to 3 nanometer, which is a few monolayer. They also observe a hysteresis loop. The coercivity is like 40 or 50 OE at the room temperature. So the message here is that transition metal actually can be magnetic. Okay? So this has important implication. I'll come back later. Okay? So since the VS2 magnetic data we just look at it is from the hydrothermal method. Okay? It's mix of chemical solution and so forth. So in our lab, we try to use a more clean-cut, like CVD method to do. We use a 2 temperature zone, okay? Put a sulfur powder, put a VCl3, so cook it up and flow with hydrogen argon. So this is the AFM of one of the flake we grow, about 6 nanometer, as you can see from the height profile, about 30 nanometer. And you can also find a flake that about 2 monolayer. Okay, it's hard to see, but that's the borderline boundary between flake and SiO2. If you look at TM cross plane view, it has a nice single crystal for each flake. And this is high resolution TM. Interlayer spacing also agree with the VS2 interlayer spacing. Okay? The problem about CVD growth is that it's not purely one thickness. So sometimes 2 monolayer, sometimes 6 monolayer. Okay? Also, the size could be different, but we are able to grow up to 100 micrometer, which is very large compared with other people's work. So originally, we thought we would use this so-called MOC, or smoke, which is developed in the 80s, which is called surface magneto-optical Curry effect, which you shine a polarized light to the sample of interest and monitor the change of polarization of the reflected light. And that change of polarization of reflected light is related to the magnetism of the sample of interest. However, as you probably can realize, because the flakes only occupy about less than 10% of the substrate, so the Kerr signal actually is not very strong. So we kind of temporarily gave that. So then we thought about maybe we can use a magnetic force microscope. So, and this is in collaboration with Dr. Shi at Park Center in Albany. Okay? So what we learned from her is that you first scan, you do a topological mapping. Okay, so this is a typical magnetic recording tape. You basically see the topological feature. Then you lift it a certain height above this first scan. Remember, van der Waals force I introduced has the 6/12 power law dependent, inversely power law. So if you lift it to a certain height, the van der Waals interaction, which allow you to probe the topology effect, that's gone. So whatever you left for the second scan at this lift height will give you the magnetic signal. Okay, so this shows that magnetic force microscopy signal. Okay, this basically indicator tracks, okay? So you can find more detail in this publication in the Park Systems website. So I'm going to show you the data collected with Dr. Shi. This is an optical image of the flake. This is scale bar, okay? So it's not the largest one, but if you scan the first scan, which is a topological height along the edge between the flake and the SiO2 substrate, it's about 4 or 5 nanometer, okay? 4 or 5 monolayer. So it's not a monolayer, okay? Now next you do the second scan by lifting this tip, magnetic tip, 25 nanometer above the first scan. You will measure this so-called magnetic phase change, okay? And that one is at 25 nanometer lift height, okay? So you can do the magnetic phase imaging at different lift height, 20, 25 is this guy, and increasing the height. Then you plot this magnetic phase shift as function of the lift height. You get a data point here. We try to fit the 612 dependent. That doesn't work because this is away from the van der Waals weak interaction, okay? Now, we cannot fit with any other power law, but this guided curve is the exponential fit, okay? And this fit actually is consistent with the magnetic interaction between the tip and this magnetized magnetic flake, okay? Because it's supposed to be, kind of decrease when you change the separation. Also, this room temperature is done at room temperature, which is agree with what the density functional calculations prediction. Okay? So actually, my original abstract has only that two topic. But I think that this is AFM conference. I have listened to many, many nice talk. The major parameter to describe a rough surface is the RMS, as we have seen in the past 2 talks. So here is a germanium 111 film deposit mica. The reason I call van der Waals is because originally we thought mica is layer material behave like a van der Waals behavior. If you look at the thickness, same film at different annealing temperature, from 300, 350, and so forth, okay? This is a kind of top view. This is a 3-dimensional view, okay? I would ask you, how do you describe this temperature-dependent film morphology? How would you describe it in words? Looks like it's rougher, right? Looks like some lateral feature also gets larger. Agree or not agree? Okay. But my question is, can we quantify it? Okay. So actually, you can quantify it. So those are the results. Okay. As you can see that the RMS, we call it omega, increases, become rougher and rougher, and lateral feature, those are feature also become larger and larger, okay? So I forgot to mention, why do we study germanium? Germanium is considered to be a 3D material, okay? Also, literature could not find germanium to be epitaxial unless you heat up to 800 degrees C. But from this study, we learned that there's a golden window about 425 degrees C. We can actually grow epitaxial germanium. I mean, literature they jump the temperature too far, every 50, 100 degrees. So they miss that window, which is 425 degrees C, okay? Now, the point I want to emphasize is how do we get those numbers quantitatively, okay? So for example, you deposit some material on a substrate, okay? They diffuse, some gets roughened, okay? So as we know, we use the RMS, omega, which is defined as height at a certain position minus average height, square root, take square root, okay? squared and then take a square root. So this basically describes what's the fluctuation, amplitude fluctuation of a surface. Then you also need this lateral correlation. Basically, you can think about as a wavelength. Okay, so this one is described the height distribution. One sort of parameter people did not realize is that even you have a same RMS, same lateral correlation, if you look locally, they could be different. So this we give a notation called alpha, called local roughness, which has a value between 0 and 1. 1 is the smoothest one. Okay? So if you have a surface that has a self-affine or mount structure or any anisotropic surface, you can use the high correlation, which is the height, okay, at certain position minus the origin of reference you choose, squared, then ensemble average of an entire surface. It has a certain asymptotic behavior when the position is very large to a certain characteristic feature that's your lateral correlation length. The value is actually 2W squared. So if you plot a high correlation function as function R, okay, at R very larger than this lateral correlation length, you get 2W squared. So from here, extract RMS. Very locally, you get the local slope that give you this local roughness X mode. In between, at the knee or turning point, that's your lateral correlation length. So we use this high correlation, get all this number, okay? So I want to emphasize more. This is just done by an undergraduate student using MATLAB. I hope this gives you the impression you need more than one parameter to describe a rough surface. This is surface height. This is the position across the surface, okay? This case, you have the same lateral correlation, but different vertical RMS, right? It's W1 smaller than W2, W3, okay? Even though this lateral correlation is same. This example is you have the same vertical roughness, but your lateral correlation length, this is larger than this, larger than this, larger than this. In this case, is that you have same vertical roughness, same lateral correlation length, but locally, if you look at the local roughness, this is smoother, this is less smooth, this is very rough. So the message here is that if you just go beyond just look at vertical roughness, you can get much more information. Okay, the last slide I want to share with you is some old work. Old work, sometimes I feel like it's really nice, okay? So this is AFM image of silicon deposit on silicon. Each one is a different sample. This one grown about half an hour. Then this you start fresh again, grow another sample, and so forth, up to 8 hours. And you apply the high correlation function I was talking about. So you plot high correlation as function the position across the surface. Okay, a quarter an hour. Okay, you got this curve. As time goes by, you got this curve. But locally, the roughness seems parallel to each other. It means local roughness doesn't change a lot. But if you look at this vertical roughness, they increase. Also, the lateral correlation feature also increase a little bit. So if we just concentrate on the vertical roughness, and you can have an electric solution, which is linear partial differential equation as function of time. The most simple case applied to thermal evaporation is a smoothing term and a noise term. Noise term exists in every deposition, no matter you have a well-controlled evaporation source or well-controlled temperature. So the smoothing effect and the noise, they always compete. Okay, that's how you determine if a surface is smooth or not smooth. So the bottom line is the solution of this linear differential equation actually gives you roughness as a function of time. This is not thickness, function of time to a certain power law. And the power law value is 1/4. So if you plot these vertical roughness you get from the experimental work as function of time, those are data point. But since it's a power law, so you replot in log-log scale from the slope, you get this experimentally determined roughness, which is 1/4, pretty close to a theoretical prediction. So to summarize, I hope I share with you two examples, which is the perovskite. Traditionally, we thought it's a 3D material grown on a layer material. And when you see the holes and cracks, don't throw it away. It's like a gold. That means you use other technique, in this case, a peer technique. You can correlate the peer's peak shift to the strain relaxation. Another example is this VS2 flake that I talked about, which using magnetic force microscopy, we learned that it has room temperature ferromagnetism. Okay? This is very important because everybody use iPhone, computer. The reading head in your computer laptop, it's actually made of a ferromagnetic material and non-ferromagnetic material, like sandwich. Okay? And imagine if you can use your TMDs material as your ferromagnetic material and put in this reading head. So you can have another dimension. In other words, everything we talk about so far, we use a charge, electron charge, in a conventional circuit, no matter field effect transistor. But if you can add a spin as another degree of freedom, okay, you have more potential possibilities. Okay? And last thing I kind of throw in, just to share with you, our learning from former students is that when you want to describe a rough surface, you need more than one vertical roughness parameter. You need a lateral correlation, you need a local roughness. Okay? Also, in principle, you don't have to do experiment do deposition for a long, long time. If you know the dominant mechanism in the film growth is smoothing effect and noise, okay, you can expect this exponent as time-dependent exponent is a quarter. So you can predict 2 hours later what will be the roughness in the vertical direction. So this, I hope, will save everybody a lot of time. Okay? I thank you for your attention. Okay.
Thank you, Professor Wang.
Yeah.
So we can take a few questions.
So everybody knows.
The MFM data was, very nice. So magnetic force microscopy is famous for not being very quantitative, as opposed to VSM. Have you done both VSM and also
Not
MFM
yet.
to try to
That's a
compare?
good question. Actually, when we first started, we tried to use the smoke surface magnetic optical curve effect, which is pioneered by Sam Bader at Argonne National Lab in the 80s. Okay? And we set up that in our lab. Actually, we can determine submonolayer iron, submonolayer cobalt, submonolayer nickel. However, in this case, because the flake is only less than 10% of the coverage, so it's very, very difficult to get a reasonable signal-to-noise ratio. That's why we switched to try the magnetic force microscopy. But you're perfect right. We will go back to do either MOC. We are in the process to refine our surface magnetic optical curve effect. Also, we have VSM in material science. But in that case, we need to make tons of flakes. Okay? I think the smoke is nice in a way that it allows to do longitudinal, also vertical. Remember, Alan was talking about when you have electric polarization or magnetic polarization, you don't know it's purely vertical or purely longitudinal. It could be tilted some direction. So for MOC, I think it's relatively easy because you can use a longitudinal mode or perpendicular, we call polar mode. Okay? VSM, you have all the flakes together. I think you see a net magnetization. You don't know it's vertical or horizontal or whatever. Okay, so there are pros and cons, but we have that in a plan. Okay, yeah.
So for the interest of time, we'll just move ahead to the next schedule. We'll have a 15-minute break that will allow you to ask more questions to our speakers. Okay. So thank you, Professor Wang. Let's give her.